Okay. Hang on. Let me move this to a bigger screen so the recording comes out nicer. Okay. So, and then I better move these over. Hang on, folks. Sorry. All my ducks in a row here. All right. So in this section, we want to look at computing what was called the Laplace transform of functions and translate the ODE into an algebraic equation. We then hope to invert this equation or invert the solutions to this equation back to get a solution to the ODE. Okay. So this is a really cool idea where we're going to translate this problem through a linear transformation called the Laplace transform to a different space. And in that space, we will be solving for a function just like we were before, but we're going to be solving for that function algebraically. We won't have to do any calculus on it necessarily. I mean, in some cases we will, in some cases we won't. But it's a completely different space, and so it might be that it's too hard to solve the IVP or the ODE in the current space, but it's easier to solve the corresponding algebraic equation. So let me just give you the picture for this. So normally we have an IVP, and really everything we're doing here is for solving specific IVPs, and we'll see why that is in a little bit. But we're trying to solve this IVP, right? We're trying to get down here to the solution, and we get stuck. There's a wall or something blocking us. We're stuck. Okay? So one technique is this Laplace transform technique. And so what we're going to do is we're going to convert this, the original IVP, into an equation involving a function f of s. Okay? So we're going to take this IVP and we're going to transform it over into this S space. So this is, I'm going to refer to this here as T space. And so whenever I'm dealing with the IVP originally, I'm going to use the variable T, and we're going to translate it into S space. So whenever I'm dealing with the transform of it, will be in S space. And so then what we're going to be able to do is, in a lot of cases, we'll be able to solve the equation for f of s. And then what we're going to do is we'll take that solution that we get and we will transform it back into our solution space. So let's go ahead and put some vocab. So really what we're interested in right now and what we're going to focus on today is these two arrows that I've just drawn. So this first arrow, we're going to go from the IVP to T space, computing what's called the Laplace transform. That's what we're going to look at here. And we denote the Laplace transform with this sort of curly script L. Okay, I'm not very good at drawing it. I've been practicing it all afternoon, but I'm still no good at it. So that's our Laplace transform. And so that's the Laplace transform. And then we're going to go backwards using the inverse Laplace transform. One of the nice things about a linear transform is, well, I shouldn't say all transformations, but a lot of transformations, when you think about it being represented by a matrix, and many matrices are invertible. So we are able to go backwards in a lot of cases with the inverse transform, and we'll see how to do that. Okay. I'd like to say a few other things. The Laplace transform certainly isn't the end-all, be-all. It's not the only way to solve ODEs. It's not always the best way to solve ODEs, but it's becoming much more popular to a method to use. You can look up, I'll let you look up if you're interested in the history of it, but I'll just say that initially engineers were using the Laplace transform for a long time. I think it was developed by a fellow named Hamilton who really started looking into it. But math people sort of held their nose against it because they couldn't figure out why it, or maybe that's a little bit strong, but math people didn't like it because they couldn't figure out why it worked. And it wasn't until the early 1900s that we developed a really solid theory to be able to talk about why this Laplace transform procedure works. And so now it's becoming more and more popular. It's specifically useful, so let me just say of particular interest, at least for what I'm going to be doing here, are nth order linear ODEs. Well, that's not too exciting. We've learned how to solve those already using the characteristic equation and method of variation of parameters or method of undetermined coefficients. What's different here is we're going to do this with discontinuous forcing functions. And that's where I think we start to see a lot of the interesting applications of the Laplace transform. So just to kind of preview where we're going to go, we're not going to solve one of these today, but what's sort of motivating what we're doing here is, so we've got our sort of our spring mass system that we've been looking at, and maybe we've got it's got drag on it. So sometimes people to show drag show this dash pot, right? So it's like a way to induce drag. So we've got this spring mass system, but then we've also got a forcing function, and we've dealt with equations with forcing functions before. Maybe we've got some sort of motor here with a piston arm, and this piston starts rotating and puts motion into the system. Well, that's nothing new. We've done that before, where in fact that was often a sinusoidal forcing function, where we've had that forcing the spring to move, but then it's got its own spring energy, and we looked at the solutions to that. But here's one way to look at it. In the real world, you don't just start off with this motor running and it runs for all time. In the real world, what happens? Well, some time goes by, and then you flip a switch on, and this motor starts running. And then you flip a switch off, and this motor stops running, but the spring is going to continue in motion. And that's far more realistic than these sort of fabricated math worlds where we say, hey, this motor has been running since the beginning of time, and it will continue running till the end of time. Let's model this spring. So learning how to map these discontinuous functions over into S space is a very useful tool for when you want to treat the realistic situations where you're flipping something on or flipping something off, or you have any other sorts of discontinuities. Some of you may have seen the Dirac delta function, and we'll look at that maybe depending on how much time we have. And we'll look at how we can map that function over into S space, and it becomes a lot easier to talk about a solution over there. Does everyone get sort of a general idea where we're going with this Laplace transform?
Yeah.
Okay. So let's go ahead and just let's go ahead and introduce it. First of all, just a transform. This is just to refresh. This is just like I've used the word transformation or operator, but here we use the word transform. I'm not really sure why we make these minor distinctions in the vocabulary. But a transform is an operation on a function that returns a new function. And of particular interest are the linear transforms, such as our derivative operator, right? That's one example. We've also seen plenty of other linear transformations in this class that we represent by n matrices. So just recall that a linear transformation T has what property? So if I do T to, in this case, I'm going to do T to functions. So if I do T to the sum of these two functions, some constant times f of x plus some constant times g of x, what does it mean when we say T is a linear transformation? It means that T distributes over the summand, whatever we mean by adding these two objects. In this case, our objects are functions, so function addition. T distributes over the vector addition, and scalar multiples factor out of it. So this is what we mean by linear transformation. Just to say one more time, even if the clothing looks a little different, this is a linear transformation where we factor out the constants and we can distribute the transform or the transformation over the sum. Okay. Any questions about the reminder of what a linear transformation is? Okay, so let's go ahead and let's suppose f is defined on the interval from 0 to infinity. Then the Laplace transform, this is what we're defining. We're going to define this transform that we need to use. So the Laplace transform, and we're going to note it this way. So there's a nice printing of it. I'm going to try to sketch that curly L, but I probably won't do the best jobs with it. Okay. Is an integral transform given by this expression here. So we're going to take the Laplace transform of a function. We do the Laplace transform to a function. How do we do it? By taking the integral from 0 to infinity of e to the minus st times our function f of t dt. So that's our Laplace transform. It's something we do to our given function. We do it to the function f, and that's going to map us over. So we're going to take this function f here, and it's going to get mapped over into S space. Okay? So let's say a couple of things about this. First of all, note, when all is said and done, the solution to this, or the expression that we're left with, is a function of S. Okay, so I'm not using S as a constant there. I'm using it as another variable. Okay. So that expression there, when all is said and done, when we're done evaluating that limit, is a function of S. Okay. What else do I want to say? I just want to note the presence of that limit. Of an infinite limit of integration. So that means that remember we learned in Calc 2, somewhere in Calc 2, you learned how to deal with limits at infinity for your limits of integration, and we're going to have to revisit that. So be careful. Okay. Notice that by the distributive property of multiplication and the linearity of integration, that the Laplace transform is linear. So I said distributive property of multiplication. We can also say that constants factor out, which is, I guess, because of the distributive property. Constants factor out of integrals. Okay? So constants factor out of integrals, and we've always been able to distribute integrals over sums of functions. Okay? Now we got to be a little bit careful with that because we've got this infinite upper limit of integration, but we can still do it. And we'll look at, in most cases, and we'll look at, or I shouldn't say most cases, but in a large class of functions, we'll be able to do this and have it be linear. So we'll see that in a moment. Okay, so I need to remind us of a few facts from calculus. Okay? So we're going to have to revisit a little bit of L'Hopital's rule. I do want to make sure that you see that the L'Hopital's rule comes into play in almost all of these problems because of that infinite upper limit of integration. So let's just look at this limit right here. We've got the limit as x is approaching infinity of x e to the minus x. So remember in calculus class, we said, hey, this has the indeterminate form infinity times 0. And whenever you've got a limit of that form, you can't just say, oh, the answer is going to be 0, or the answer is going to be infinity. You have to analyze it in greater detail. And usually our trick for analyzing an indeterminate form is to apply L'Hopital's rule. Well, to apply L'Hopital's rule, we need to first rewrite this as x over e to the x, because now this has the indeterminate form infinity over infinity. That's one of the forms for which L'Hopital's rule applies. So now we can go ahead and apply L'Hopital's rule, and we're left with the limit as x approaches infinity of 1 over e to the x. And so what does this limit come out to be?
One over infinity.
So I want to be a little careful saying 1 over infinity. I want to say 1 over an
arbitrarily large number.
Which then approaches what?
0.
Which approaches 0 then. Okay, so I would discourage you guys from writing that in your math.
Remember, it's a powerful hammer. Don't go around looking for nails.
Yep. Some of you learned the L'Hopital's from me. All right. Now, I want to look at this next example, where we have to be a little bit more careful here. So now let's look at the limit as x approaches infinity of x e to the minus ax. Okay. In this case, what we do depends on the sign of a. if a is greater than 0, then the limit we approach what? If a is, sorry, if a is less than 0, sorry about that, let me say that. If a is less than 0, then what do we approach?
Infinity.
Infinity.
Yeah. If a is less than 0, a is a negative number, and I've got a negative sign in front of a, then that makes that whole expression positive as I plug in positive values for x. So we get e to a positive number times a positive number. And so where is this going? This will be approaching infinity. But if e is less than 0, or if a is less than, if a is greater than 0, then it's the same as before. And we get that this limit and the limit as x approaches infinity of x e to the minus ax will be equal to 0, but there's some work happening behind the scenes, and I need you to be aware of the work that's happening behind the scenes with L'Hopital's rule. Okay, this is an indeterminate form. This is still the indeterminate form, infinity times 0, but you guys are getting big enough that we can just go ahead and say, hey, folks, in a tug-of-war match, who wins, exponentials or polynomials?
Exponentials.
Yeah, does that make sense when I say that, folks? When you get this, so what's happening here in this structure? Let me zoom in on that. X is approaching infinity, e to the minus ax, if a is positive, is approaching 0. Okay, so you've got a tug-of-war match. One factor is getting bigger while one factor is getting smaller. Who always wins the tug-of-war match eventually for large enough values of x? An exponential function does. Okay. So let's go ahead and then make this conclusion, because I don't want to have to evaluate this limit too much the long way. So the last thing I want to say is that the limit is x approaches infinity of x in e to the minus ax. That's going to equal infinity if a is less than 0. Or I guess we can even say a is less than or equal to 0, I guess. But it's going to equal 0 if a is greater than 0. And that's by performing L'Hopital's rule n times. So I don't want to do that each time. I want to be able to just look at something like that and say what its limit is. But I want you guys to be very aware of what's happening behind the scenes there. I don't want you to just say, hey, we've got an indeterminate form, that limit comes out to be 0. And I will try to always pause and point that out as we do these Laplace transform problems. Okay. So we've been talking about these Laplace transforms. Let's do the simplest Laplace transform of them all. Let's do the Laplace transform on the constant function 1. So here we go. This is our first chance to practice this. We've got the Laplace transform of 1 is equal to, well, what was the definition of the Laplace transform? It's the integral from 0 to infinity of e to the minus st times the function dt. Okay. So I do want to revisit how you handle infinite limits. If there's something that you need to learn to start being careful of going forward in your math and physics careers and engineering careers, it's being very careful with infinite limits. Okay. So just to emphasize that, this is how we taught you how to do it in Calc 2. We said that's the limit as beta approaches infinity of the integral from 0 to beta of e to the minus st dt. So we put a variable up there, then we evaluate the integral separate from the upper limit of integration, then we take the limit. There's a sequence there that's vitally important going on in math. Okay? We have to first evaluate the integral with a definite value, beta, and then take the limit as beta goes to infinity. Okay. So we can evaluate this integral. We're left with the limit as beta approaches infinity of minus 1 over s e to the minus st evaluated from 0 to beta. And then plugging in those limits of integration, we're left with the limit as beta approaches infinity of minus 1 over s e to the minus s beta minus parentheses minus 1 over s e to the minus s times 0. So we're left with, let's go ahead and just talk our way through the rest of the problem. This term right here, we've got s's and betas. Folks, what's my limiting value? Beta. So just be careful with this. There's a lot happening here. We've got s's and betas. My limiting value is beta. Okay. Will this limit, this first term here, will that always converge? Will e to the minus s times a large number.
That's an alternating series, right?
Not really a series. We're not adding anything up here.
Depends on the sign of.
Oh,
Depends on the sign of s.
Yeah, it's harmonic, right?
No, so there's no series here. There's no.
Oh, okay.
Yeah. Yeah. So Ben's right. It depends on the sign of s. This limit goes to infinity. So notice that this will either be infinity if s is less than or equal to 0. I think I should just say less than 0. This will go to infinity if s is less than 0. Notice s can't be 0 because that 1 over s there. So if s is less than 0, and this second term will go to, or that first term will go to 0, and I'll just be left with plus 1 over s if s is greater than 0. Okay. So the way we usually then write the Laplace transform for this is we say that the answer is 1 over s for s greater than 0. Because we're not interested in this integral function if it doesn't converge. If the integral doesn't converge, it's useless to us. So we're only interested in where it converges, and it converges to 1 over s. And when does it do that? It converges when s is greater than 0. Okay. So let's say that we've actually, I mean, it seems like, okay, wow, we've taken the Laplace transform of the simplest thing we can, and that took us quite a lot of talking. These sort of stack up like dominoes, though, because notice now I could ask you to do the Laplace transform of, say, 9. Well, that's just equal to 9, the Laplace transform of 9 times 1, and constants factor out of a linear operator, and we just said that the Laplace transform of 1 is 1 over s, so what's the Laplace transform of 9?
9 over s for s greater than 0.
9 over s, and Edward's exactly right. We got to add that s greater than 0 there. So already now we can do the Laplace transform of all constants. Okay? Well, now we just need to learn how to do the Laplace transform of all the remaining functions. So here we go. We're not going to get to them all. We'll do a few of them, we'll look at it, and then we'll take them from tables after that. All right, so what I'd like you to do is go ahead and start trying to take the Laplace transform of t using the definition on the previous page. So go ahead and get started on that. What are we going to have to do in this problem, folks?
Can we pull that t out in front of the integral?
Oh, heck no. Oh, heck
Didn't
no.
think so. Didn't think so.
What are we integrating with respect to?
T.
T, so it's a constant. So no, no.
Integration by parts.
Yeah, we're going to have to do some integration by parts. Let's first rewrite this as the limit as beta approaches infinity of the integral from 0 to beta. So I'm being kind of pedantic here right now, folks, because I want you to review this because it is a fundamental part of your math career going forward, is dealing with these upper limits. And then as Chris says, we're going to have to do integration by parts. Actually, so I'll leave that beta there. I'll leave the integral symbol here as we do integration by parts. So let's see here. We're going to let u equal which term, folks? Which factor?
T.
T. And that gives us du equals dt. And then our dv then is going to be e to the minus st dv, or dt. And so that makes v equal to minus 1 over s e to the minus st. Oof, I didn't give myself enough room. It's all right. Well, it's huge. I can't tell how big I'm writing sometimes, folks. All right, let's see here. So this is equal to the limit as beta goes to infinity of the product of u and v. So u is t and v is minus 1 over s e to the minus st. All of this is going to get evaluated from 0 to beta minus the integral of v, which is minus 1 over s e to the minus st du, which is just our dt. Cleaning this up, we get the limit as beta approaches infinity of, that's a times there, folks. I didn't emphasize that. So we get minus t over s e to the minus st. And then let's see, this would be a plus sign. Then we're going to divide it by another factor of minus 1 over s. So minus 1 over s squared e to the minus st. And all of this gets evaluated from 0 to beta. Do you have a question there?
No, sorry, I forgot to mute.
That's all right. That's all right. Okay. So folks, let's write this out in gory detail. So this is going to be the limit as beta approaches infinity of minus beta over s e to the minus s beta minus, then we evaluate that at 0, so minus 0 over s e to the minus s times 0. That's just took care of the upper and lower limits for the first term. Okay. Then we get minus 1 over s squared e to the minus s beta. That's for that second one. And then there'll be a plus sign. Watch those minuses and pluses. It's so easy to mess up on these. Plus 1 over s squared e to the minus s times 0. Okay. Now, I don't think that we should be too concerned. I think everyone should feel comfortable that term goes to 0 because we evaluated that t over s at 0. Okay. Also, this will go to 0 if s is greater than 0. And there's not really any concern there because remember, we're taking the limit with respect to beta. So we're plugging in a large positive number from beta. And as long as that e is to a negative exponent, that entire term will die off. The hard limit is which one? This one right here. Okay. That's the more complicated limit, and I just want to re-emphasize what's going on there, folks. We're not going to show it because I don't want us to have to write this much more than we already have. But L'Hopital's rule is what we would need to justify that this limit will go to 0 only if s is greater than 0. Otherwise, it goes to infinity, in which case we have no interest in that expression. Okay. And so we're left with just 1 over s squared. So a lot of work to show the Laplace transform of t is 1 over s squared.
And that's when s is greater than 0, right?
Oh, yes, very good, very good. Yes, this only holds for s greater than 0. Now, it doesn't look like, I mean, it looks like, hey, maybe s could be negative based on the domain of this. But no, we made the assumption for convergence in the middle of doing these limit problems that s had to be positive. Yeah, thanks for adding that, Edward. Okay. So we're building our library of Laplace transforms here, folks. So this one's not too bad. I'd like you all to try C. C is actually probably the easiest one, the second easiest one we do after A. So go ahead and try C. And by easy, I don't mean that you should just look at it and know it, but at least it doesn't involve any integration by parts or anything like that. So go ahead and try C here.
Well, I noticed it's the opposite sign of what we were doing earlier, what we were proving earlier with the, instead of negative a times t, it's just positive a times t.
Well, but that's for, so A here stands for a constant.
Okay.
And S is a variable.
Okay.
Yep. Yeah, so just sort of stick to the script here of saying the Laplace transform is, and then all you're going to do differently here is you're going to replace that t with e to the at, and then you'll see how things clean up. So folks, this is it's been a while since we've done such hefty integration. Okay, if you're rusty on it, first of all, if you're struggling with this, and it's so hard because I can't see anybody's faces. If you're struggling with this, my guess is you're having trouble actually with the integration and not with the new concept. Okay, so try to separate what's the new concept. That is setting up this integral right here. That's the only part of the new concept that we're dealing with right now, is how to set up that integral where it's always 0 to infinity e to the minus st times whatever function we're working with. But we've seen before, when you multiply e to a function and then you try to integrate it, you could be up for a lot of work. So try to separate the steps of integration from the new material here. Okay, I want to look at this statement that I've currently got. Notice that the only place where beta shows up is in this first term, and beta is going to infinity. I want this term to converge. If a minus s is positive, then the whole thing diverges. Because we've got a positive exponent, and the exponent continues to get larger, and so it's going to tend towards positive infinity. But if a minus s is less than 0, then what? This whole first term dies off. If a minus s is negative, then that whole first term dies off, and we're just left with minus 1 over a minus s. Okay? Let me just rewrite that. I'm going to distribute the negative to the denominator, and so we get 1 over s minus a, and this holds if what? If a minus s is less than 0, what's another way to say that? Another way to say that is if s is greater than a. So we have convergence if s is greater than a, and that's the Laplace transform for e to the at. Okay. Folks, I want you guys, so here's your first submission. I want you to go ahead and do the full steps for the Laplace transform of sine of at. Okay. If you get stuck, well, first of all, you should try it on your own. If you get stuck, here's, I don't know if you guys know Khan Academy, there he is. I found a video of him doing the same thing. I didn't want to do it because it takes a long time. It takes about 20 minutes. But there's a video of him working through it. And so that's what I want you to submit for next time. The Laplace transform, or for, actually, I think I want you to submit it by Friday night. Okay, so this is due by Friday. So I highly encourage you to do it just right after class here, by Friday at 11:59 p.m. Okay, because I don't want too much time going by between this lecture and when you first try to take your own Laplace transform. Okay, I want you to do it using the direct method. Okay, I don't want you to try any shortcuts or tricks. But if you're interested, this is a video of a faster way of coming up with that Laplace transform, which uses the complex numbers in an interesting way that we've seen before. And we get the Laplace transform, both the sine and the cosine right away. Okay. So taking on faith, I should add to this, we need to add here for the Laplace transform, you should add to this, this holds if s is greater than 0. That's what the domain of it is. So it only holds if s is greater than 0. Sorry, I should have added that. Okay. How are we doing? Are there any, we've done a few of these now. I've been going kind of fast. This is tough integration. How are we doing? What questions do you have? What concerns do you have over this procedure?
So from here, basically, you're kind of giving us the building blocks, and now we have we know what the Laplace is for certain functions, and so we can basically invert them to come up with a solution for actual problems.
Yeah, so you're on the right track. We're going to take the Laplace transform. We will see that gives us a functional equation, and we will solve for that function. And then we will, as you said, we're going to invert it back to give the solution to the original IVP. And we will get to one of those examples here at the end of class today. Okay. So I want to show you that we've actually done quite a bit of work. We can now find the Laplace transform of this function right here. The Laplace transform of this function would just be 3 times the Laplace transform of t minus 2 times the Laplace transform of the sine of 4t plus 3 times the Laplace transform of e to the 2t minus 7 times the Laplace transform of 1. So that's all using the linearity of the Laplace transform. So each one of these we've already done. This gives me 3 over s squared minus 2. I guess we haven't done this one, but here's the rule for it right up above there. Minus 2 times 4 over s squared plus 16 plus 3 times 1 over s minus 2 minus 7 times 1 over s. And you could then clean this up. By the way, when I said clean it up, I mean you could go ahead and combine constants. You do not normally want to combine this as a single fraction. In fact, our goal, because we want to do the inverse, will be to try to we will want to keep this in its partial fraction decomposition form. So that technique of partial fraction decomposition is about to rear its head again. We'll see it on the next page, maybe 2 pages. Okay, so this is tedious stuff, folks. And you do need to be good at integration, because that's, you guys are in math and science. You got to be good at integration. It's tedious stuff, though. So I went ahead, here I've shown the work for doing the Laplace transform for t squared. So here's a nice chance for you to look at it. Let's see here. There's the definition. All we did was replace the f of t there with what we're currently taking the Laplace transform of. Now, because I'm dealing with upper limits of integration, I need to put a limit there. And then what I went ahead and did was I evaluated this. You've evaluated this I'm sure you've done this very integral several times before in your Calc 2 careers. Okay? It's a little bit messier with that s as opposed to a number. But I went ahead and integrated it by parts. Okay? I want to note something, that when we did it integration by parts the first time, we end up with a factor of 2t there, right? Because we'd let u equal t squared, so our du would be 2t. So that's where that 2t shows up, right? And we're not done with the integration by parts, so we would again let let u equal, in the next time we do integration by parts, we'd let u equal 2t, and then we get du is equal to just a 2, which is where that 2 shows up. And folks, if you don't have this printed out, that's okay. I'm recording this, so you'll be able to copy down these notes or something. So don't feel like you have to quickly write out all the steps of this integral. Maybe just jot down that this is number 9 and make your notes to yourself there. Okay. Now, folks, if we'd started off with a t cubed, right, we would have let u equal t cubed, and then we would have had du was 3t squared, right? And then we'd have to do integration by parts again. We'd let u equal, the second time, we'd let u equal 3t squared, and then our du would be 6t dt. I guess I forgot the dt's on those. Okay. And then we do integration by parts one more time, and we'd let u equal 6t, and that would make our du equal to 6. Pay attention to these numbers here, the numbers 2 and the number 6. Those are special numbers. Okay. All right. So the last step is, there's that integral, and we need to evaluate it at the upper and lower limits of integration. So what I want to emphasize is that here we would have the limit as beta approaches infinity of negative beta squared over s, e to the minus s times beta, plus negative 2 beta all over s squared e to the minus s times beta, plus negative 2 over s cubed e to the minus s beta. And then we'd subtract from that a bunch of terms that have t's in them, with t going to 0, because that's our lower limit of integration. And what's the one term that survives out of all of that? It would be a minus 2 over s cubed when I let that t go to 0. Did that a little fast. I went ahead and dropped off all the terms where I inputted a 0 for a t as a polynomial. And this is the term where I just inserted a 0 for t there, and there was no t in the rest of the expression. And then notice that each one of these goes to 0, but we'd have to do L'Hopital's rule on both of these. We'd have to do LH once here. We'd have to do LH twice here. And then this one will go to 0 here, but that is all assuming what? S is greater than 0. And so at the end of the day, what does this Laplace transform evaluate to? It evaluates to be 2 over S cubed. And that holds for S greater than 0. Okay, so I don't want to do this forever. So I want to clarify something. On your next exam, I will ask you to do some Laplace transforms by definition. When I say by definition, you need to go to this integral statement. Okay? So I'll ask you to do some by definition, but most of the time, folks, you're just going to look them up in a table. Okay, so that's the comment that I make right here. In the homework, pay attention to whether you're asked to do the definition of the Laplace transform or asked to use properties / theorems in order to find the transform. Okay. So let's go ahead and based on what we sort of saw here, let's go ahead and see if we can do the Laplace transform of the generic power function. The Laplace transform of t to the n, which we would compute by doing the integral from 0 to infinity of e to the minus st times t to the n dt. Well, you may see where this is coming from. We ended up with 6 if we did for t cubed. We ended up with a factor of 2 there if we did it for t squared. If we did it for t to the 4th, we would end up with a 24 there. And so what we're ending up with is n factorial over, and notice what the power on s is. The power on s that shows up is always 1 more than the power we started with. So this is our formula for the generic power function. And you can see that because of the way you have to keep integrating by parts, and every time you integrate by parts, when you roll down the power by integrating by parts, you bring down first like a 5, and then you bring down a 4, and then you bring down a 3. That's where that factorial is showing up in that expression. Okay. So here are some rules for doing the Laplace transform. Okay. First of all, keep in mind that it's linear. And then here's the Laplace transform of a power function of E. We derived those two already, we derived the C already. Here's the Laplace transform of sine. That's your homework, is to prove that one. Here's the Laplace transform of cosine. And then here's another one that just to give you a sense of, if you look in the back cover of our book, you'll see that it's just filled with, I can show it to you. Yeah, you got in the back cover of the book, there's a whole page just showing you Laplace transforms. Okay. I don't want you to always be deriving these, but I also need you to know where they come from. So that's why I'm going to sometimes ask you to actually derive them. But I'm not going to have you derive something that requires you to do integration by parts 3 times. That would be unnecessarily long. Okay, so let's go ahead and look at number 13 here. And let's use the Laplace transform to find the Laplace transform of f of t. Where f of t is this cubic function. Okay, so we want to go ahead and, I don't know how to do a chain rule. Let's make sure that makes sense. I can't do a chain rule with the Laplace transform, right? Or I don't have chain rules, maybe the wrong word, but this is a composition of functions here. And I don't know how to do the Laplace transform of a composition of functions. The best I can do is expand it out term-wise, or I could go back to the definition. I think the best thing to do is to expand it out term-wise. Let's see here. So we get t cubed plus 2 times 3, so plus 6t squared. 3 times 2 squared is plus 12t, and then plus 8. So there's that function in expanded form. And so how do we take so I'd like you to all take the Laplace transform of this. You don't need to derive it. Use the rules up above. Go ahead and take the Laplace transform of this. So when I do this, let's see here, we're going to have 3 factorial over s to the 3 plus 1 plus 6 times 2 factorial over s to the 2 plus 1 plus 12 times 1 factorial over s to the 1 plus 1 plus 8 times 1 over s, the Laplace transform of 1. You can jump straight to the answer for these folks. This is 6 over s to the 4th plus, let's see, that's 4, or that's 2, so 12 over s cubed plus 12 over s squared plus 8 over s. Any questions about how we just did that? Okay. Let me try to motivate you for where we're going with this. Let's consider this piecewise function right here. F of t is equal to 0 if 0 is less than or equal to t, which is less than a. It's equal to 1 if a is less than or equal to t, which is less than or equal to b. And it's equal to 0 if t is greater than b. So here we have a piecewise function. It's discontinuous, right? This is a discontinuous function, and I would not like to see that as my forcing function on the right-hand side of an ODE, because it would mean I'd have to break it up into a bunch of separate parts, and I'd have to solve it as sort of a chain. I would use my initial conditions from the first piece, get me to the second piece, figure out what the new initial conditions would be, solve the second piece, plug in those new initial conditions. I'd have to do a whole chain of a problem in order to solve something like this. Okay? By the way, the graph of this, just to make sure, you want to make sure that you're up on your piecewise functions. The graph of this function would look something like this. Here's A, here's B, and it's 0 between 0 and A, and then it's 1 between A and B, and then it's B from, or 0 again from B to infinity. So there's the graph of this function. Sometimes this is called a boxcar function, I think. It might be called a square wave function, something like that too. So this is a very discontinuous function. Let's mention one thing real quick. I'm never going to worry about those endpoints when I'm doing this, right? So I'm never going to worry whether one of those dots is open or closed, because as far as the integral is concerned, values of integrals don't recognize the value at a single point. Okay, so we don't have to worry. You might represent you might be looking at a problem and you might choose to represent it this way, whereas your friend might close this dot and open this dot. It doesn't matter. Okay. All right. So let's go ahead and do the Laplace transform of this. The Laplace transform of f of t, which is equal to the integral from 0 to infinity of e to the minus st f of t dt, is equal to, and now what am I going to do, folks? Well, this is a piecewise function, and so to integrate it, I have to integrate it over its separate pieces. So we'll have the integral from a to 0 of e to the minus st times 0 dt, the first piece. Oops, excuse me, folks, I got that limit of integration incorrect. That should be 0 to a, plus the integral from a to b of e to the minus st times 1 dt, plus the integral from b to infinity of e to the minus st dt. Oops, sorry, times what? Times our unknown function, which is what? Or times our function right here, which is what in this case?
0.
0. Good. So folks, this first integral evaluates to be 0. The second integral gives us minus 1 over s e to the minus st evaluated from a to b. And the third integral gives us 0 here. So what's our solution? Our solution would be minus 1 over s e to the minus bs. Somebody might be feeling that right now. Plus 1 over s e to the minus as.
Yep.
There you are. Folks, I think this is decently interesting. Okay, and this is what I was trying to say early on. We're going to be doing these Laplace transforms. We'll solve some ODEs that we've already been able to solve before. But I think that this is pretty interesting that here we have this function in t space is discontinuous. This function is t space is discontinuous. But its Laplace transform is about as nice a function as we could hope for. It's a combination of exponential functions, a very continuous function in S space. And that's one of the benefits for what we're doing. A lot of functions that are discontinuous in T space are continuous in S space, and so they are easier to work with. Okay, I've got 3:30. Let's go ahead and take a, do you mind if we just do a 5-minute break here, folks, and we'll start up at 35?
No worries.
Sounds good.
All right, let's do a 5-minute break here, and I'm going to grab some water, but then I'll be back to answer your questions.
My questions are what?
Folks, are there any questions?
We all have our video off. He can't tell if we ever come back or not.
Yeah, that's true. I might just be lecturing into the void, but it's often what we do.
I'm just sitting here like this.
Oh no.
I don't even know what my questions are.
So the biggest thing so far is that we're just taking this expression right here. And we're just evaluating it as we plug in different functions for f. And generally, it's pretty tough to do that. Most functions are pretty tough to evaluate in the Laplace transform. We often use integration by parts and other techniques. The hard part is then also that we've got this upper limit of integration of infinity, which is always a pain to deal with. You guys want to know, I'm sitting here, I was watching some videos on partial differential equations last night, which is not something I know very much about. And I was watching a series of lectures from this professor in this international university, and very quiet, very thoughtful man. And he would keep saying, "It's clear, isn't it?" And he was like telling us that it was clear in the lecture. And I thought it was really, it's clear, it's clear. And
MML does that all the time. Like it'll explain some intermediate step and be like, clearly it's this. And I'm like, how'd you get to that?
now the joke is that you get two mathematicians arguing whether or not a point is clear or not, whether it's trivial, whether it's obvious that they should be known. And the one who thinks that, no, I don't think this is clear at all, goes to his office, works on it for 5 hours, comes back and says, yeah, you're right, it's perfectly clear. All right, folks, let's go ahead.
The least funny joke I have ever heard.
Oh, that's a good math joke.
That was funny.
I thought it was funny.
I liked it also.
That's all right.
Yeah, it was clearly funny.
Thank you, Lord.
Oh, just fuck right off.
All right, folks. I'm going to go ahead and let's go ahead and talk about this notation here real quick. So instead of writing the Laplace transform of f of t, because it's always giving us some expression in S space, we're going to represent it by capital F of S. Okay. So again, the picture that goes with this is we've got a function here in t space, f of t, and then we do the Laplace transform to it, and it gives us a function over here in S space that we're going to call capital F of S. So we're connecting the two functions together by using the same letter. So you know that little f goes with big F, little g goes with big G, but notice the difference in the domain value. This is in T space, this is in S space. Okay. I'd like to return to 16, but if I don't get to it today, that's something we can quickly pick up next class period. What we're going through is we're talking about, well, can we always do this? And it turns out, no, you can't always compute the Laplace transform, but under some pretty large, with some pretty large general restrictions, yeah, we will be able to compute it. Okay. So we now want to talk about the inverse Laplace transform. Okay. I don't want to talk about this too much other than to say that if these conditions that I'll talk about next time are met, then the Laplace transform is 1-to-1, and so it is invertible. 1-to-1 or unique. Okay. Put in the language of linear transformations, the kernel equals 0. Okay. So anyway, we'll talk more about that next time, but in the cases where I give you a problem and ask you to do it, you will be able to invert the Laplace transform. Okay. This first example, we'll work through it. I don't think it'll be too bad. The second example is going to be quite a bit more challenging. Working backwards with the Laplace transform is sort of like taking the Laplace transform versus going backwards is sort of like the difference between taking the derivative and integrating. It's a lot harder to go backwards with them. It requires some ingenuity. Not that going forward was easy, but it was at least something like, okay, I understand I'm taking an integral. Going backwards involves sort of saying, hey, let me guess this, let me try this, let me tinker with this. Okay, so what function do you think, when we take its Laplace transform, gives us 120 over s to the sixth? So we're going backwards here, folks, and we can do it term-wise. What function, when we go backwards, by the way, we write this Laplace L inverse for the inverse Laplace transform, just the one that goes backwards. There's the arrow notation pointing that out. Okay. So what function, when we took its Laplace transform, gave us 120 over s to the sixth?
T to the fifth.
T to the fifth, yeah.
It's t to the fifth. Remember, because what's the Laplace transform of t to the fifth? It's 5 factorial over s to the 5 plus 1. Yep, sure enough, that gave us s to the sixth. And then 5 factorial, folks, is 120. I do recommend having your factorials memorized through 7 factorial. That's just good business. Just like you should know, like, you know, the cube root of 32 is, or the cube root of, or the fifth root of 32 is 5, is 2. So you should have a few of these factorials memorized. I recommend memorizing up through 7 factorial. So if any of these numbers show up, you recognize them as a factorial. By the way, the Wikipedia page on 5040 is fascinating. Highly recommended. All right. I'm not getting any laughs today. You guys are all grumpy about this. All right. How about for s to the fourth underneath 48 there? What do you think it should be? Like, so one thing you might want to do is try to get the expression right and worry about the constant after a moment. So what should that probably go with, folks?
T cubed.
Yeah, it should probably go with t cubed, right? But when we do the Laplace transform of t cubed, we get 3 factorial over s to the 3 plus 1, so s to the fourth. But 3 factorial is only 6, and we need to somehow get a 48 there, so we need to divide 48 by 6. So this is going to give us 8t cubed, going backwards. This is something, folks, it'll get easier the more you do. So let's see here. I think this is the Laplace transform. That's straight up the Laplace transform for just t squared, right?
Straight up.
Straight up. Because it would be, what's the Laplace transform of t squared? It would be 2 factorial over s to the 2 plus 1. So yep, we're good to go there. And then how about this one, folks?
7.
7.
7.
7. Very good.
I won.
Very good. All right. The hard ones to work backwards from are the sines and cosines, in my opinion. Those are the hardest ones to work backwards from. So we're going to practice that here. And then you'll get some practice in the WebAssign for this. Okay. This is one of those things that I like to say. I use this phrase sometimes. Give yourself what you want and then pay for it. Okay? So when you're trying to work these problems, I say give yourself what you want, then pay for it. Let's see what
Like
I mean.
wine.
What's that?
Like wine.
Like lying? Sure, lie. Fudge the numbers a little bit, but then you're going to have to pay for it right after that.
She said wine.
I did say wine.
Oh, okay, yeah, sure. Okay, that works too. Wine, lying, yeah. So folks, what do we think this should be? Let's go back up and look at our Laplace transform rules, which we're just now learning. Here they are. Here's a bunch of them. Which one does it look like?
E.
Well,
I mean, 7 isn't a squared thing, though.
yeah. But look at what's in the numerator of E. An S, which is a variable, right?
Oh no.
Would this just be a t cubed, or sorry, t plus a constant?
No?
Or
A
It's
D.
D.
I think it looks closest to D there. Okay, let's go back and look at the structure of that. Okay. It looks like it's not an A there, but it looks like we've got a number over S squared plus a number. A number plus S squared over a number. Okay. Well, the thing I can't really adjust, although we could do some crazy completing the square, the thing I can't really adjust is this value right here without doing some complicated adjustments. So let's go ahead. We're going to look at the Laplace inverse transform of just this one piece, 1 over S squared plus 7. And I'm going to first rewrite it as the inverse Laplace transform of 1 over S squared plus the square root of 7 squared. Do we agree with that?
Sure.
So it looks like our A would be the square root of 7, right?
Yes.
I really wish I could print this.
I'm sorry.
Because then you wouldn't have to scroll back and forth for me to see it.
That's okay. That's okay. I have to scroll back and forth to remember it. Does that look like what we have there, folks? We've got the A squared, yeah, plus the S squared, yeah, but what do we need in the numerator?
We need a root 7.
We need a root 7 in the numerator. So go ahead and give yourself what you want there. But then what? Give yourself what you want, but then you got to pay for it. So then we put 1 over root 7 outside of the Laplace transform. Does that make sense?
Oh, yeah, that makes sense.
If you like, folks, let's you don't have to change this if you're happy with stuff, if things are making sense. I'm going to go ahead and take all the inverse Laplace notation out, and we'll just worry about that in just a moment. So all I'm going to do is say that, hey, we could take 1 over S squared plus 7, and then write it as 1 over S squared plus the square root of 7 squared. For this to be meaningful, I need a square root of 7 upstairs. That's something I could take the inverse transform of, but I didn't have that square root of 7 in the denominator, so I pay for it by putting it in the denominator. Do you see that if you canceled those radical 7s, you'd be back to the other side of the equal sign?
I'm good on that part.
Okay. So what does that mean? That means that the inverse transform of this first term is 1 over the square root of 7 times the cosine of the square root of 7t. That's the function that when we take its Laplace transform will map us to this first term here. All right, folks, be careful.
Sine or cosine?
Sine. Sine. Thank you, Evan. Sorry, folks.
Here's your sign.
What's that?
Here's your sign.
Here's my sign. Yeah. Sorry about that, folks. That should be sign there. Let me just double check. I'm sorry. I'm doubting myself. Yeah, cosine has the S, sine does not. Okay. All right. So there's the first one. Now we're going to take the inverse transform of 4 over 5s plus 2. Folks, don't miss the big picture. What type of function is this going to translate back to? A sine? A cosine?
I don't know because I can't see the list.
What's it going to translate back to? A sine? A cosine? Clean up that list.
Looks like an exponential, probably.
Probably an exponential. That's something to be very, I mean, you should go to that right away. If you have s minus something, you don't have s squared, right? We've got s minus something, then it's probably going to be an exponential. So pay attention to whether it's got an s squared plus something in the denominator or just an s plus something in the denominator. If it's just an s alone, it's going to come back as a power function. But if it's s plus something or minus something, it'll come back as e. And if it's s squared plus something or minus something, it'll come back as a sine or a cosine. So this is going to, we expect this thing to come back as an e. So to remind us of the e rule, we said that, hey, the Laplace transform, Laplace transform of e to the minus a, it was just e to the a, of e to the at was 1 over s minus a for s greater than a, right? So we're going to try to somehow use that rule. Well, notice I don't want a 5 there, so let's factor that 5 out of the entire denominator. So that gives me 4 over s plus 2/5. And we don't want a 1 in the upstairs, so that gives us 4/5 times 1 over s. And here I'm going to rewrite this as minus 2/5. And from there, we can see that this is going to, when we take the inverse transform of this, it's going to bring us back to 4/5, because the constants just come along for the ride, e to the minus 2/5 t. That's for that second term there. So we get plus 4/5 e to the minus 2/5 t. Okay. Folks, I want to do some more practice on these. I'm going to challenge you to try to get the last two. The last two are going to come out to be minus 2 cosine 2t plus 3 sine 2t. That's how you can break these last two up. And if I get a chance, I'll come back to this at the end of class and show you how to do that. But I want to make sure I get to this final example. Okay. Does anyone have any questions about how we did the E one? Oh, I'm getting some muffle from someone.
That was my dog.
Oh, great. Good, good. He objects or he agrees?
She's mad that she's being made to nap.
Gotcha. All right, folks. By the way, it may not seem like we're getting very far here, right? Okay, if it's got an s squared in the denominator, we can take it back. If it's got an s in the denominator, we can take it back. What about an s to the 5th or an s to the 6th? Well, don't forget what we've already done in this class with partial fraction decomposition. By the fundamental theorem of algebra, any polynomial can be broken down to factors of quadratics and linears. And we know how to handle quadratics, they're sines and cosines, and we know how to handle linears, they're e's. So for any rational expression, we now know how to do the inverse transform. Now, sometimes that might be very difficult. It might involve some complicated factoring, some complicated completing the squares, but any polynomial can be broken down into quadratic terms like this one, or linear terms, and by partial fraction decomposition, we can further break them apart into separate pieces and invert those pieces back separately. So your ability to do Laplace transforms, the inverse transforms, often boils down to your ability to do partial fraction decomposition. So I want to go ahead and show you, I tried to make it sound like something you read on the internet, right? Learn partial fraction decomposition using this one weird trick. It doesn't always work. So I made you guys review partial fraction decomposition at the beginning of the course because you need to know the long way of doing it, because that's how we do variation of parameters. It's how we do a lot of other techniques in this class, so you might as well review it. But when you have partial fraction decomposition of linear factors without multiplicity, there's some quick shortcuts to doing that doing that decomposition. So we know that we expect s squared plus 6x plus 9 over s minus 1, s minus 2, s plus 4. We know that we want that to look like something over s minus 1 plus something over s minus 2 plus something over s plus 4. Normally what we do, just as a reminder, don't write this part down, normally what we do is we put A, B, C, and then we do all the work to figure out, we come up with a system of equations and we figure out what A, B, and C need to be, right? Is that ringing a bell, folks?
Yes.
Yep. Makes sense.
All right. So normally that's what you do for partial fraction decomposition. And it's what you still have to do if you've got a quadratic term. So if we had s squared plus 9, if you had a quadratic term, or if you had a repeated root like s minus 1 quantity squared. If you had either of those, then you can't use this one weird trick. Okay. Did I show this to you guys last time?
I don't think so.
Okay, good.
Man.
All right, so here's how you do partial fraction decomposition the fast way. Okay. Let me see if that's not gonna work. Okay. I just realized you guys can't see me, see what I'm doing. I'm going to find, I'm going to take, for this first one here at, for this first factor here at -1, I'm going to replace all entries of s with 1, the thing that would make this expression 0. I'm going to replace all entries of s with 1, and then I'm going to I'm going to block this out and then replace all the s's I see with a 1. When I do that, notice that my numerator would be 1 squared plus 6 times 1 plus 9, and in the denominator we'd have 1 minus 2 times 1 plus 4. Does everyone see what I just did there? I replaced all the s's with 1. So let's see here. That gives us 15. That gives us 16 in the numerator. And in the denominator, we get minus 5, it looks like, a -5. So we get 16, -16 fifths will be that entry right there. Let's continue. So to find the next entry in the partial fraction decomposition, so I'm sorry, folks, I can't show you. Normally what I do is on the board, I cover up the factor, but we can't do that here. So for the next entry, I'm going to cover up the factor of 2, and I'm going to replace all of the s's that are remaining with 2's. So in the numerator, notice I get 12 and 9 is 11 and 4 is, I think I get 25 in the numerator. And in the denominator, if we replace everything with 2, we've got 6. So we get 6, I think.
That's what I got.
Great. So folks, everyone see how I'm using this technique? You can, I mean, you know, if it's too bad that people aren't doing cocktail parties right now, because you could impress all your friends on a Friday night.
You can totally make online classes into drinking games with your classmates.
It's a good idea. We should try that next week.
I already
I don't
had
know how
a
well
classmate
that'll go.
suggest it for OChem. Like, already had a classmate suggest it. I'm like, yeah, that would probably improve our experience of that course dramatically.
Oh no, well, hopefully it improve mine, but all right. So the last one, we're gonna replace all the s's with a -4, and so I'll let you guys do that. think I get 1 over 30. I was doing that kind of quick. Is that what you guys got?
Yeah, that looks right.
Yeah, so it's just a gimmick, but it's really worth it for the work that we're about to do here, to be able to quickly partially decompose. Now, if they're quadratic factors or if they're repeated factors, this won't help you. You're back to the old-fashioned way of coming up with a large system of equations. Hopefully, some of them work out nicely. But what I like about this, folks, is, again, remember, any polynomial or any rational function can be broken down by partial fraction decomposition down to either linears or quadratics like we had here. Any one of these large expressions that I give you, even if it doesn't factor nicely, even doesn't play nice, they can, by the fundamental theorem of algebra, be broken down into a sum of smaller rational functions where you've either got linears or quadratics in your denominator. Okay. So we're not ready to do all the, or I'm not ready to show you everything yet. We're going to do that next time. We just don't have enough time. But here are a couple of nice little facts that we're going to prove next time. And that is, when you do the Laplace transform of the derivative of a function, you get s times the Laplace transform of that function minus the function evaluated at 0. Okay. I don't think you can see the pattern there. Here it is for the Laplace transform of the second derivative.
But Mr. Von Tagen, are
Yeah.
you saying when you take the Laplace of a derived function, or when you take the derivative of a Laplace function?
This is the derivative. We're taking the Laplace transform of the derivative of our function f.
Thank you.
Yep. And where this is going is that this is our unknown function f that's going to show up in our differential equation, right? So we might have, it might be, you know, the Laplace transform of y prime. When we don't know what y is, we still can write its Laplace transform as an expression involving just the original function. And we'll prove that next time. It's actually not very hard at all to prove.
So that so it's s times capital F of x. What's that variable x?
Ooh, that should not be there. That should be f. That should be s. Sorry, folks. That should be. I'm sorry. That should be an s there.
S times capital F of s, right?
That's correct.
Okay.
Good
Folks,
catch, Evan.
That's
Good
an
catch.
S there. Yeah, very good catch. Okay. So I don't think you can see the pattern from just the first one. Let's look at the Laplace transform of the second derivative of a function. The Laplace transform of the second derivative function is s squared times capital F of s minus s times our initial condition minus the second initial condition. Okay. Or here, I think it's not until 25 that you really start to see the pattern. When you take the Laplace of a third derivative, you get s cubed times the function minus s squared times the initial condition minus s times the initial derivative minus just the initial second derivative. And then you can take it larger than that. So let's go ahead and we'll go ahead and do this one. I think we've got time. So let's go ahead and give the Laplace transform of the fourth derivative of something. So take a moment, give the Laplace transform, just follow the pattern that you see up above. Someone disappeared. I get a ring when people leave, but I don't know who left.
Uh-oh.
Uh-oh, wow. That's how it goes. Okay, folks. So any questions on how we just did this? Yeah, I'm not too concerned if you're still a little bit shaky about this. We're going to do this next time, but I really wanted to show you this example. So we're ready to now take the we're going to go ahead and solve this second order IVP, and we're going to do it using the Laplace transform. So I know this is one that you guys could just solve very quickly using the characteristic equation, but this is going to be our tactic going forward. This is the whole point of doing Laplace transforms, is to solve these IVPs. What will be more interesting is when we have more complicated functions here, discontinuous functions in T space, but when we move them over to S space, they'll be continuous and they'll be easier to work with. So here we go. I'm going to go ahead and take the Laplace transform of both sides of this equation. Okay. You can already see how this immediately will carry over to non-homogeneous equations. You'll take the Laplace transform of that right-hand side there. Okay. On the right-hand side, the Laplace transform of 0, though, is just 0. Nothing exciting there. And I'm going to run out of room. Let me start with the left-hand side. So on the left-hand side, we're going to get, following this formula up above here, we're going to get s squared x of s. Okay, so notice I'm using the capital letter X there. That's not, I mean, if you get that wrong, it's not the end of the world, but since I've got the little letter X for my unknown function, I'm using capital X there. Okay. So we've got s squared capital X of s minus s times fx of 0 minus x prime of 0. All of this is the Laplace transform of x double prime.
What happened to the 6?
So yeah, so I haven't, all of that's just the Laplace transform of the second derivative expression here. So, yep. Yeah, so then let me get to the next term and then hopefully I'll clear it up. So we get minus the Laplace transform of x prime, which is just s x of s minus x0. Okay, careful here, folks. I should be a little more careful with my capitals and lowers. That's a lowercase x of 0. Okay, and all of this is the Laplace transform of x prime. Minus, there's this 6 times, we don't know what the Laplace transform of x of t is because we don't know what x of t is, but we'll just write capital X of s. This was the Laplace transform right here of x. And that all has to equal 0. So let's clean this up. We get s squared x of s minus, let's see here, s0 is 2. So we get, oh, did I mess it up? Just a second here, folks. S prime. X is 0. Come on.
Are we hoping some stuff is going to add out?
No, I just, this isn't working out the way I worked it beforehand. I'm just not sure whether I was right then or I'm right now. So I'm trying to check something. Oh, there it is. Never mind. There. No. 2s. Where did it go? There's all that. 6s s squared. Yeah, I dropped it. Okay. Oh, it's not a problem. Okay. I made a mistake, but it's okay. All right. Sorry, folks. S squared x of s, and then we've got minus s times x naught. So we've got minus 2s there, minus x prime naught, which is a minus 1, minus s x of s, then plus x naught, and x naught is 2.
Plus 1, Charles, if you're minusing a minus 1 on your x prime term, further back.
Minus a minus 1, plus 1. Thank you. Thanks, Christine.
I got one.
Good, good. And then minus 6x of s, and that needs to equal 0. Folks, what are we trying to do here? All right, so I just want to, you don't need to go anywhere. I'm going to take us back to the very first page where he said this was the idea. We take an IVP, that's what we started with. We moved it over into S space. That gave us an equation involving f of s. We're going to solve that equation for f of s, which will give us an expression in terms of just s, and then we're going to invert that back to t space with the inverse transform. Okay. So I'm going to solve this expression here for x of s. So collecting all my x of s terms together, we've got s squared minus s minus 6 all times x of s is equal to, and then taking the other terms over to the right-hand side, we get 2s minus 3. Okay. So continuing to solve for capital X of s, we get 2s minus 3 all over s squared minus s minus 6. And our denominator factors as s minus 3 times s plus 2. Now, all I need to do then is take the inverse transform of this expression. Well, I think it's hard to take the inverse. Let me give you a chance to catch up. Sorry, go a little fast. Are there any questions about the work I've done so far?
No.
Any questions, folks? Anyone else?
No, but from here, are we going to do the decomposition again?
Yeah, so here's the thing, right? If I just happen to be able to look at this thing and say, oh, I know what its inverse transform is, then you're welcome to apply it. But I don't know what the inverse transform is of this large expression here, so we want to decompose it into little pieces. That'll be easier to work with. Okay? So we're going to use that one weird trick for partial fraction decomposition. Why can I do that? Because I've only got linear factors and none of them are repeated. So I'm going to cover up the s minus 3 factor and replace all of the s's with a 3. And when I do that, I get 6 minus 3 is 3 all over 5. So I get 3/5 over s minus 3. Using that cover-up technique. For the other one, for the over s plus 2, I'm going to cover up the s plus 2 and replace all of the s's in that original expression with a minus 2. When I do that, I get minus 7 over minus 5, or I get 7/5. All right, it's been a long, long class. There's a lot of hard work in this class today. And now we're ready for the kind of the punchline of the joke that's been this past hour and a half, or 2 hours. What function, when we took its Laplace transform, gave us something like 1 over s minus 3? What is the inverse transform of that?
Exponential.
The exponential, specifically e to the 3t. Exactly. And so we get that when we do the inverse transform to this, and now I'm going to take the inverse transform of both sides. On the left-hand side, I get x of t. I'm back to x of t land, right? That's not really that exciting. But on the right-hand side, I get 3/5 e to the 3t plus 7/5 e to the minus 2t. And there we have the particular solution to this IVP. Ta-da. Now, you can check your work, because this was an easy IVP, right? You could check your work because the characteristic equation here is r squared minus r minus 6 equals 0. And the roots of the characteristic equation are r minus 3 and r, or factors this way. So the roots are r equals 3 and r equals minus 2. So you already know the general solution is c1 e to the 3t plus c2 e to the minus 2t. And then you could go ahead and solve for your initial condition, or your constants there. But the point was that we were able to do all of that without ever solving finding a solution to that ODE. We're still able to find the IVP solution. And that's the technique of the Laplace transformation. Again, the benefit isn't that we were just able to do it for this easy function right here that we learned how to do over a couple months ago. The benefit is that on this right-hand side, we could have some discontinuous forcing function. Or in some cases, we may even have a nonlinear function here. We might have some extra factors of t there. And we know how to take the Laplace transform of t. Okay? Now, there it's a little bit more work because you've got t times x double prime. You can't just do it factor-wise. So we got more work to do if we want to solve more complicated IVPs. But that's our general strategy in this method of Laplace transformations. So just to take you back to the first page. Just to take you back to the first page, there is that's the general strategy. If we're trying to solve an IVP and we hit a wall, we go around by taking the Laplace transformation, building a function in terms of f of s, solving that function for f of s, and then inverting that function back into t space. All right. Any announcements? Yeah, so I am asking you to do the Laplace transform of S of AT. You've got the two videos together, go together to make a video solution. I think it comes out to be about 18 minutes total, 19 minutes total for that video solution. Okay. I would encourage you, though, to try it on your own. Don't jump straight to the video solution. Rework some of my examples first. Then try the transform of sine of AT. So that's something I'd like you to submit by Friday because I don't want too much time to go by. Okay? So please submit that by Friday. Like I said, it should take about 20 minutes to watch the videos and do it. Maybe add another 10, so you're talking about a half an hour for that problem at the most. Okay. Additionally, folks, I went ahead and the web work. Sorry, that's the wrong company. The WebAssign is all set up for all of the stuff from the systems of equations that we did. That's all due on Monday. Okay? Please, folks, get that done as soon as possible because I want to go ahead and release to you some Laplace transform WebAssign so you can get started on those because you'll want to practice those, and it's nice to have that immediate feedback. Okay. What else? I think what I'd like to do is, can you guys see my calendar? Here we are at the 16th. I would like to have, I know it's getting close right back to finals week, but I would like to have an exam over what we've covered on Laplace transforms and the systems of equations. I'd like to do that, on Tuesday the 28th. Okay. So on Tuesday the 28th, we're going to do the third exam for this class. We're going to do the third exam for this class, and then we won't have the final too much after that, but that way we'll have an exam that's just on these two topics, systems of equations and Laplace transformations. Any questions, folks? So again, we're going to do that third exam on the 28th of April. So I'll be getting an exam review to you guys out next week.
Sounds good.
All right, folks, I've done some updating in the grade book. Please take a look at the things I've graded. Make sure that everything seems all right to you. And just be working on those web assigns because those are going to be, that's going to be the bulk of what you're submitting for homework going forward, except for these occasional submissions that I have you do in D2L. So.
I was really excited thinking that a B was still within reach for me until today's class.
I wouldn't hold that. I wouldn't discount that. Remember, we dropped the lowest test score and
You replace it if the final is higher.
Yeah. So I would say it's still well within reach. Still well within reach.
Killing me.
Other questions or comments, folks?
I have a small question.
Yeah, cool.
So it says in the corner of my screen that you're recording this. Like, where can I find these recordings?
Yeah. Let me stop it now.